1-3 AP Physics by Zach Speaks the Science Geek. Since this is the first video in the series, I'll be introducing how each video will be set up, as well as covering the first topic of study, vectors. So each video is going to begin with a discussion of the topic in a theoretical sense, and then important formulas will be introduced. There'll be several questions in each video, and each video will end with an FRQ. So let's begin with our study of vectors. What is a vector? A vector is simply a quantity with direction and magnitude. It's usually represented as an arrow. It has x and y components. Many quantities in physics are vectors, such as force, velocity, and acceleration. And so along the bottom you see many examples of vectors. So what can you do with a vector? You can add them, you can multiply them, you can do something called vector resolution, where you decompose the vector into x and y components, and you can find the magnitude and angle of the vector by using the x and y components. So we're going to take a little detour into understanding what makes up a vector. So each vector is made of x and y components. They're at right angles and they make a right triangle. This means we can use the Pythagorean theorem and sine, cosine, and tangent with the vectors, as this little model shows the x and y components and the little original. So the direction of the vector is usually going to be measured from right here, where the original and x touch, right by where the laser pointer is. And so that means tangent would be y over x. And so if we knew the y and the x components, we'd use tan inverse y over x. So tan inverse y over x to find the direction, and x squared plus y squared equals r squared to find the magnitude. That should look familiar because it's the vector form of the Pythagorean theorem. It's x's and y's instead of a's and p's. So we said we could add vectors, and here's one way to do it. It's called the graphical method, or the head to tail method. You take the vectors and you're basically going to move this blue vector so its tail touches the head, like this diagram, and you're just going to connect the two. So this orange vector would be the new vector. It's the vector you got from adding the two. And again, it makes a triangle. If you had more than two vectors to be added, it wouldn't make a triangle, but in this case it does. And so then the other way, the numerical way to add vectors, is you take the magnitude of the vector, you multiply it by the sine of the direction to find the y angle. So if we go back to our little diagram, it'd be finding this component, which is exactly how it's labeled. And then we'd use cosine to find the x component. And then we'd add the x and y components of each vector that we want to add up, and then we'd unify it into one vector by using these properties right here. So the other thing we said we could do with vectors is we can multiply them. You have three ways. One isn't listed because it's pretty simple. The first way is multiplying it by a scalar. That's the one that's not listed. It's basically if you had one vector and you multiply it by 3, you have 3 times the magnitude, but no change in direction. So it's just 3 of the vectors and you lay them end to end. You have the scalar or dot product, which results in a non-vector quantity, a scalar, like a number. It's 1, 2, 3. It doesn't have a direction. And then that's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. And the other way is the vector or the cross product, which results in a vector quantity. And it's the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. So let's start working on some problems. Add these two vectors, 2 30 degrees northeast and 3 60 degrees northeast. I'm going to work through this one both graphically and numerically, but in the future I'm just going to do it numerically. So here's our first vector, 2 30 degrees and 3 60 degrees. And so I take our graph and I construct the two, and then I connect it like so, and there's our new vector. On a side note, You'll find it easier if you plan on using the graphical method. You're going to find it a lot easier to use polar paper because the directions, the degree measures are usually labeled, and it'll be a lot easier to find like 2 or 3 or 5 than like, because the numbers won't match up exactly like they would on a Cartesian plane, but if you use polar they would. So it'll be helpful if you decide to use that. Here's the numerical method. As we said, you just take the magnitude times the direction, the cosine of the direction or the sine of the direction, and then you add them up, like here, and then you use these properties to find the magnitude and direction. Okay, here's our second problem. This one is what I was talking about with the scalar. It's just 2 times the vector b, so it's would have the magnitude of 10 units, but still the same 225 degrees. So you add everything up, you would see that this one is actually 0 because these two are in the opposite direction. And so this is, I use this problem to illustrate that the negatives do matter. So cosine of 225 is not the same thing as the cosine of 45. It's the negative of the cosine of 45. And so that would lead this to cancel, and so there's no magnitude and no direction. Problem 3. An airplane is traveling at 250 kilometers per hour, 58 degrees northwest, and the wind is blowing at 45 degrees southwest at a speed of 22 kilometers per hour. And our question is, what is the real speed and direction of the airplane? And so we decompose it into vectors, like shown. There's our x and y components. Add everything up. So it's negative 148 kilometers per hour in the x direction and 196.5 kilometers per hour in the y direction. And then we do the square root of those things squared and then added together. And we would get 246 kilometers per hour, 53 degrees northwest. Problem 4. A swimmer is traveling 0.5 meters per second due east across a river. The current is 2 meters per second due south. What is the swimmer's real speed and direction? So decompose into vectors, then into x and y components, add up, simplify. So 2.06 meters per second, and the direction is 76 degrees southeast. Okay, part 1. An aircraft is traveling at 240 kilometers per hour, 23 degrees northwest, and the wind is blowing at 23 kilometers per hour, 48 degrees southwest. What is the real speed and direction of the airplane? What would happen if the speed of the wind was increased? What would happen if the speed of the airplane was increased? This one is a theoretical problem. It's not going to give you a concrete number, and it's just asking what would happen. So would it be faster? Would it be slower? Would it be closer to the plane's original heading? Would it be closer to due south? What? And how fast would a third wind need to be blowing if it was directly opposing the aircraft in its path of motion for the aircraft to be forced to land, if aircrafts are forced to land if they're traveling less than or equal to 200 kilometers per hour. So I made up that number. Don't think that's correct or anything, but that is just an example to show you a bit of an application of vectors. So pause the video, work through things. I'm going to start walking you through the solutions in 3, 2, 1. Okay, so here's the x and y components added up. Here's the magnitude and direction. This problem's just like the two other ones we did. It's pretty simple. Part 2, if the speed of the wind increased, the direction would be focused more towards the west and the speed of the airplane would increase. And if that kind of doesn't agree with what you thought, you can always try plugging in numbers. So plug in, instead of 23 as this problem would be, try 33 or 53. Just if you use a bigger number, you would see. And then if the speed of the airplane increased, the direction would be closer to the plane's original path and the speed would increase. You can see that the direction would change if the vector's magnitude change, because in this case there'd be more in the y component to counter the airplane's y component, so this would be closer to 0 and it'd be closer to due west. And then here, the airplane's components would both be bigger, so these components would be relatively smaller, and so then these components would be closer to just 240 or whatever cosine of 23. Okay, and then part 3, the last part. So we take the properties of the airplane, negative 240 cosine 30, no, sorry, my bad, negative 236.3 and 76.7, the components in the direction of motion, and then those would combine with the wind's components to add up to the 200 cosine 18 or 200 sine 18. And then, just like we've been doing, we would add all these up, except now we have an unknown variable, right? But it's only one unknown, so it's just a linear equation. We should all know how to simplify those. So here's the linear equation for the x, and if you solve for r, you should get that r is about 48.3. So if the wind was blowing at 48.3 kilometers per hour, the plane would either be forced to land or to shift its heading. So there you go, a little bit of an example. And so next week we'll be covering kinematics, the study of motion. Hope you all will watch that video. See you then.